Assalamualaikum and good day to everybody. So today we will continue our chapter 4 transformer with the basic concept, the overview and the construction of transformer. So transformer is an electrical device which used to convert AC electrical power at one voltage level to AC electrical power at another voltage level without a change in frequency. The application of transformer, it is widely used in electrical power system. For example, this is a three-phase transformer which is used to convert the voltage, for example, from generation to transmission, which use a step-up transformer, and then from transmission to distribution and to the load, the step-down transformer will use to step down the voltage for that is suitable for the usage at the load. So usually the important task of the transformer is to change the voltage and the current levels in power system. Another application is in single phase transformer, which is used in many electronic applications such as washing machine, television, laptop, handphone charger, and many more. The basic transformer construction can be seen in this figure. In its most basic form of a transformer, it consists of a primary coil or winding. So this is the primary coil, a secondary coil or secondary winding, and a core that support the coil or winding. The composition of a transformer core depends on the voltage, current, frequency, the size limitation, and the construction cost. For the types of transformer construction, it can be in core or in shell. For core form, the windings are wrapped around two sides of a laminated square core. For the shell form, the windings are wrapped around the center leg of a laminated core here. So the most efficient transformer is shell form transformer. For the lamination of the transformer, this is the laminated steel core and this is toroidal steel core. So the lamination is to reduce the eddy current losses, and hence it can increase the efficiency of the transformer. So what is ideal transformer? Okay, so the following assumptions are made in the analysis of an ideal transformer. First, the transformer windings are perfect conductor, which means it has zero winding resistance, and the core permeability is infinite. That means the core reluctance is zero, and all magnetic flux is confined to the transformer core. That means there is no leakage flux, and the core losses are assumed to be zero. Okay, so the ideal transformer can be seen in this figure. The magnetizing current will flow through the primary windings when it is connected to the AC voltage. So this magnetizing current is lagging the voltage by 90 degrees. So the magnetizing current will produce the flux, okay, and this will induce the primary and secondary EMF, electromotive force. So this EMF also lagging the flux by 90 degrees. So the magnitude of primary induced EMF and the voltage supply is the same, but 180 degrees out of phase. So the sinusoidal primary current will produce a sinusoidal flux with the equation given as this equation, and therefore the induced voltage can be obtained, which is equal to this equation. And at the maximum induced voltage or induced EMF, we obtain it is equal to N1 omega psi m, which is equal to 2 pi f multiplied with N1 multiplied with psi m. And for the RMS value, we obtain this equation N1 omega psi m divided by SERT2 for RMS value. So this will equal to 4.44 times frequency times N1 times psi m. So now we obtain for the ideal transformer. So E1 in the primary side, which is equal to 4.44 times frequency times the number of turn N1 times psi m. And then for the secondary part, it is equal to a similar equation, 4.44 multiplied with F multiplied with the number of turn at the secondary winding multiply with psi m. In the equilibrium condition, the input power will be equal to the output power, and this condition is said to be ideal condition of a transformer. So we obtain the input power is equal to the output power, and hence we get this equation where V1 divided by V2 is equal to I2 divided by I1. So from the ideal transformer circuit, we note that E1 is equal to V1, voltage at primary, and E2 is equal to V2, which is voltage at the secondary part. So now we obtain the induced EMF at primary part divided by induced EMF at the secondary part. This is equal to V1 divided by V2, which is equal to N1 divided by N2, which is equal to I2 divided by I1. And this is actually equal to voltage transformation ratio. So the voltage transformation ratio will determine whether the transformer is going to be stepped up or stepped down. So voltage transformation ratio, if the A is bigger than 1, where the number of wire winding N1 is bigger than N2, so this is step down transformer. Whereas if A is less than 1 and the number of wire winding N1 is less than N2, so this is a step up transformer. So now we can summarize the equation for the transformer where the voltage at primary divided by the voltage at secondary, so this is equal to N1 divided by N2, which is equal to A. So A is the transformer turn ratio. So we know that N1 multiplied with I1, this is equal to N2 multiplied with I2. So we can also state I at secondary divided by, I at primary divided by I at secondary, this is equal to 1 over the turn ratio of the transformer. So the application of step-down transformer in electrical distribution network, the step-down transformer is used to reduce the voltage from a medium voltage, for example 11 kV or 33 kV, to low voltage, for example 415 volt. In other application, it is used to reduce the plug voltage to 140 volt to low voltage in electronic equipments, such as in radio, in phone, laptops, adapters, and many more. Whereas the application of the step-up transformer is employed in a power plant to increase the generated voltage and send the voltage to the transmission line. To calculate power in ideal transformer, we can use the power triangle to obtain the active power, reactive power, and apparent power. So this is the active power, this is the reactive power, and this part is the apparent power. So the power factor can be obtained here, where the power factor is equal to cos theta. So from here we obtain the active power is equal to V multiplied with I multiplied with cos theta, or the power factor. And the reactive power is equal to V multiplied with current multiplied with the sin theta, and the apparent power is equal to the voltage multiplied with the current. By using the power triangle, we can also calculate where S is equal to sert P squared plus Q squared. Since the primary and the secondary winding of ideal transformer have the same power factor, and therefore we obtain the active power out is equal to the active power in, and the reactive power out is equal to the reactive power in, and the apparent power out is equal to the apparent power in. And the output active, reactive, and apparent power can also be expressed in terms of current and impedance, and therefore we obtain P out is equal to P in, which is equal to I squared Z multiplied with cos theta. Q out is equal to Q in, which is equal to I squared Z multiplied with sin theta, and S out is equal to S in, which is equal to I squared Z. And we know that the impedance of the load, which is Z, is equal to resistance plus J reactance. And in complex form, we can obtain this equation where Z is equal to the magnitude of Z multiplied with cos theta plus J magnitude of Z multiplied with sin theta. And the apparent power S can also be represented in complex power, which is S is equal to P plus JQ, which is equal to VI cos theta plus JI sin theta. So now we can conclude when I1 is flow in the primary wire, it will induce magnetic flux in the core, and hence we obtain E1 is equal to minus N1 d psi over dt, and E2 is equal to minus N2 d psi over dt. So this is at the primary coil, and this is at the secondary coil. Okay, so this is based from the Faraday law. And from here we obtain E2 over E1 is equal to N2 over N1, and from this equation we can write E2 is equal to N2 divided by N1 multiplied with E1. Okay, so this is also equal to E1 divided by the transformer turn ratio, and the transformer turn ratio A is also equal to I2 divided by I1. For the power balance, N2 N1 multiply with I1 from the primary coil is equal to N2 multiply with I2 from the secondary coil. Okay, and I repeat, for the power in ideal transformer, we know that P in is equal to V1 multiply with I1 multiply with cos theta 1, and then at the secondary part, P out is equal to V2 multiply with I2 multiply with cos theta 2. But we know that in ideal transformer, the power factor at the primary is equal to the power factor at the secondary, and so theta 1 is equal to theta 2, and therefore we get P out is equal to P in, which is equal to V1 multiply with I1 multiply with cos theta. And then similar to the reactive power, so for the reactive power, Q out is equal to Q in, which is equal to V1 multiply with I1 multiply with sin theta. And then for the apparent power, S out is equal to S in, which is equal to V1 multiply with I1. Okay, so we can draw the power triangle which is P, Q, and S, and from here we can obtain that P is equal to I squared R, Q is equal to I squared X, and S is equal to I squared Z. Okay, and then by using the power triangle, we obtain S is equal to P plus JQ, which is also equal to VI cos theta for the complex power plus J VI sin theta. Okay, and for the impedance Z is equal to R plus JX, where R is the resistance and X is the reactance, and using the complex number, we obtain Z is equal to the magnitude of Z multiply with cos theta plus J magnitude of Z multiply with sin theta.
From Faraday's law, we know that E1 is minus N1 d psi over dt, where psi is equal to psi m sine omega t. And thus, we get E1 is equal to minus N1 d psi m sine omega t over dt. And we obtain minus N1 omega psi m cos omega t. Okay, and this is also equal to N1 omega psi m sine 90 degree plus omega t. And this is equal to 1 at E1 maximum. And hence we obtain E1 maximum is equal to N1 omega psi m. Okay, if we change to RMS value, so we get E1 is equal to E1 maximum divided by SERT2. So we obtain N1 omega is equal to 2 pi f multiply with psi m divided by SERT2. Okay, so we get E1 is equal to 4.44 psi m N1 multiplied with the frequency, and this is also equal to 4.44 multiply with the area of the core multiply with the peak value of flux density multiply with the number of turn. If we refer to the primary, so we number of turns should be referred to the primary side and multiply to the frequency. So this is the equation for the EMF of the transformer. Now look at example 1. A single phase transformer has 400 primary and 1000 secondary turns. The net cross-sectional area is 60 cm squared. If the primary winding is connected to 50 Hz supply at 500 a volt, calculate the induced voltage in the secondary winding and calculate the peak value of flux density in the core. So first we calculate the induced voltage in the secondary winding. So we use the formula E2 divided by E1 is equal to V2 divided by V1, which is equal to N2 divided by N1. And thus we get the induced voltage in the secondary winding is equal to V1 N2 divided by N1. So we get 500 multiplied with 1000 divided by 400 turns. Okay, so this is equal to 1250 volt. For the second part, the peak value of flux density in the core. So we know that if we refer to the primary side, E1 is equal to 4.44 multiply with the frequency, multiply with the number of turn at primary side, multiply with the peak value of flux density in the core, and multiply with the area of the core, the cross-sectional area. So if we put all the value here, we can calculate for the peak value of the flux density B. Okay, so B is equal to 500 divided by 4.44 multiply with the frequency, multiply with the number of turns, multiply with the cross-sectional area, 60 times 10 to the power of 4. So we get the peak value of the flux density in the core is equal to 0.938 Weber per meter square.
Look at example 2. A 25 kVA transformer has 500 turns on the primary side. So this is N1 and 50 turns on the secondary winding, which is N2. The primary is connected to 3000 volt. This is V1, 50 Hz supply. Find the full load primary current, the induced voltage at secondary winding, and the maximum flux in the core. So for the solution, we want to find A is to calculate the full load primary current, which is I1. So we know that S is equal to VI, and from here we can calculate for the full load current. So I is equal to 25 kVA divided by 3000 volt. So we obtain the full load current is 8.33 amp. Okay, for B, calculate the secondary voltage. So we know that the turn ratio A is equal to N1 divided by N2, and this is equal to I2 divided by I1. And straightforward, we can calculate for the induced voltage, where I2 is equal to 500 multiply with 8.33 divided by 50 turns. So this is equal to 83.3 amp, and therefore we can calculate for the voltage. So E2 is equal to E1 multiply with I1 over I2. So this is equal to 3000 volt, 8.33 divided by 83.3. So the secondary voltage is equal to 300 volt. So this is step down transformer. To calculate the maximum flux in the core, let's say we refer on the secondary part. So we obtain E2 is equal to 4.44 multiply with the frequency multiply with the number of turn at the secondary and multiply with the psi m. Okay, so the voltage at secondary is 300, 4.44, the frequency is 50 Hertz, the number of turn is 50. So from here we can obtain the maximum flux in the core, which is equal to 27 milliweber. Okay, to obtain the impedance transformation through a transformer, we know that Z load is equal to V load divided by I load, the apparent impedance of the primary circuit of the transformer, and hence we obtain Z prime load is equal to V load over I load. Okay, and we know that the primary voltage V1 is equal to A V2, and the primary current I1 is equal to I2 over the turn ratio, and therefore the apparent impedance Z prime load of the primary, this part at the primary side, is equal to V primary divided by I primary, which is equal to A V secondary divided by I secondary over A, and this is equal to A squared V secondary over I secondary. So we can also write the equation as Z, the apparent impedance of the primary side, ZL apostrophe is equal to A squared ZL. So this is equal to A squared ZL. Okay, that's all. Thank you. So next we will discuss on real transformer. Okay, thank you and Assalamualaikum.